Right now, in a laboratory somewhere in the world, an embryologist is staring down the eyepieces of an inverted microscope, just holding their breath.
Yeah.
And in their left hand, they're controlling a microscopic glass straw with a polished tip to hold a single human egg perfectly still.
Just locked in place.
Right. And in their right hand, they're maneuvering a hollow glass needle. And when I say needle, I mean, I want you to picture something so unfathomably small that it makes a human hair look like a giant redwood tree.
Oh, absolutely. A human hair is what, about 70 microns thick?
Exactly. And the internal diameter of this glass needle is roughly 5 microns.
It's just wild to think about.
It is, because inside that 5-micron space is a single, immobilized human sperm. And the embryologist is about to drive that microscopic glass spear directly through the outer shell of the egg, breach its delicate inner membrane, and deliver that single sperm directly into the cellular cytoplasm.
No swimming, no chemical signaling.
None of it. No natural selection. We are forcibly opening the door to human conception. So, welcome to our 6th deep dive in our Inside the IVF Lab series. Today, we are exploring the absolute edge of biological intervention. We're talking about ICSI.
Intra-cytoplasmic sperm injection. It really is the ultimate, one-cell procedure. When you actually watch it happen on a monitor, there is this almost profound sense of trespassing.
I like that word, trespassing.
Yeah, because you're watching two distinct, highly specialized cells being mechanically forced together in a way that biology, well, it just never intended.
So our mission for this deep dive is to meticulously unpack the physics, the chemistry, and the real operational reality of how this is actually achieved in the lab.
Exactly. We have to look at what this procedure solves, the extreme fluid dynamics and micromechanics involved, and this is crucial, the rather stark biological barriers that even the sharpest glass needle just cannot overcome.
Right. And I want you, the listener, to hold on to a central paradox as we navigate this material today. ICSI looks like science fiction.
Oh.
And on a technical level, it is a marvel of human engineering. It appears to guarantee success because it bypasses almost every natural hurdle of fertilization.
But it's not magic.
Exactly. The deeper we go today, the more you will realize that behind this apparent mechanical simplicity is a massive, incredibly complex chain of biological uncertainty.
Because just putting the sperm in the egg doesn't mean the egg actually knows what to do with it.
Right. So let's establish the foundation. In our previous deep dive, number 5, we explored conventional IVF.
Controlled co-incubation.
Yeah. We put thousands of prepared sperm into a droplet with a cumulus enclosed oocyte. We just step back. We let nature take its course. We let the biological machinery of the sperm do the work of finding, binding, and penetrating the egg.
And ICSI is the complete polar opposite of that paradigm. Intra-cytoplasmic sperm injection. I mean, literally injecting a sperm inside the cytoplasm, the aqueous interior of the cell.
It fundamentally reroutes the biology of fertilization.
It does. To grasp the magnitude of this shift, you have to consider what a sperm has to do in conventional IVF. It doesn't just, bump into the egg and slide inside.
Right, the egg has a shell.
A very thick, rubbery glycoprotein shell called the zona pellucida. For a sperm to breach that shell naturally, it has to bind to specific receptors.
ZP3 and ZP2 glycoproteins, right?
Exactly. And this binding triggers something called the acrosome reaction. The head of the sperm is basically carrying this payload of digestive enzymes, primarily hyaluronidase and acrosin.
Like an acid payload.
Yeah, it bursts open, spilling these enzymes to chemically melt a tunnel through the zona pellucida while simultaneously thrashing its tail to physically drive itself forward.
It's a chemical drill and a physical battering ram working at the exact same time.
Right. And the amount of cellular energy, the ATP generated by the sperm's mitochondria, required to sustain that thrashing and drilling is just immense.
And that is exactly where the problem arises for a lot of patients. And why ICSI was such a revolutionary development when it was first successfully performed back in the early 90s.
It was a total lifeline.
Specifically for severe male factor infertility, right?
Yes. Before ICSI, severe male factor infertility was largely just an unsolvable problem in reproductive medicine.
Wow.
If a patient had, say, severe oligospermia, meaning an extremely low sperm count, maybe only a few thousand sperm in an ejaculate instead of millions.
Right.
conventional IVF would fail because you simply didn't have enough sperm to create the critical mass necessary to digest that outer shell.
The drill couldn't get through.
Exactly. Or consider asthenozoospermia, where the sperm are present, but their motility is completely compromised.
So they might twitch in place, but they can't swim.
Yeah, they lack the progressive, forward-swimming kinetic energy required to physically drive through the zona pellucida.
And it gets even more extreme with surgically retrieved sperm.
Oh, absolutely.
Like, if there's a physical blockage preventing sperm from entering the ejaculate, urologists can go in and surgically extract sperm directly from the epididymis or the testicles.
Right, TEAS or PISA procedures.
And I was reading through the clinical guidelines on this, and those surgically retrieved sperm have essentially zero chance of fertilizing an egg on their own.
None at all.
Because they haven't passed through the epididymal transit, right? Which is this biological maturation process where they acquire the biochemical ability to swim and bind to an egg.
They are biologically immature. They're completely unequipped for the natural obstacle course. If you put testicular sperm in a dish with an egg, just nothing will happen.
Yeah.
The same applies to cases of unexplained prior fertilization failure.
Which has to be so frustrating for patients.
It's devastating. Sometimes a couple goes through a conventional IVF cycle. The sperm looks perfect on the semen analysis. The count is high. The motility is excellent. The eggs look healthy.
Everything looks great on paper.
Right. But the next morning, the embryologist checks the dish and absolutely none of the eggs have fertilized.
Wow.
There is a hidden molecular defect, maybe a failure in the acrosome reaction, or a defect in the sperm's binding proteins. ICSI bypassed all of that overnight.
The outline for this material uses an analogy that I think really clarifies the sheer scale of the bypass here.
The city analogy.
Yes. Conventional IVF is like taking someone, dropping them off in the outskirts of a massive, sprawling city, and telling them they need to find one specific house on their own with no map.
Good luck.
Right. They have to make the long journey, navigate the obstacles, locate the correct address, figure out the lock on the front door, and force their way inside.
So in this analogy, the city is the fluid environment of the dish, the specific house is the oocyte, and the locked front door is the complex biochemistry of the zona pellucida and the membrane.
Exactly. ICSI, by contrast, is like picking that person up in a helicopter, flying them over the entire city, bypassing every single street and obstacle, dropping them directly into the living room of that specific house, and locking the door behind them.
You've completely removed the burden of navigation and entry from the individual.
The embryologist operates the helicopter.
The embryologist performs the transit, the binding, and the penetration. The sperm is entirely passive in the ICSI process until the exact moment it's deposited inside the cytoplasm.
Which naturally leads to a massive question for you.
Yeah.
If this helicopter method is so effective, if you can virtually guarantee that the sperm reaches the living room, why wouldn't every single IVF clinic just use ICSI for every single patient?
That's the million-dollar question.
Right. If the goal is creating an embryo, why risk the sperm getting lost in the city? In reviewing the global data, the utilization rates of ICSI are actually really fascinating.
They vary wildly.
Yeah, in some regions and clinics, it's used in nearly 100% of cycles. In others, they try to limit it to only the most severe male factor cases. So is it strictly biology, or is there a clinic culture aspect at play?
It's both. The variation in clinical application is one of the most hotly debated topics in embryology. It touches on biological philosophy and laboratory workflow.
Break that down for me, the biological philosophy first.
So, biologically speaking, conventional IVF is a natural selection mechanism. Out of tens of thousands of sperm placed around the egg, only the most biochemically sound, morphologically perfect, and energetic sperm will successfully navigate that shell.
The best of the best.
Exactly. And the egg itself plays an active role in selecting its partner through chemical gradients. When we use ICSI, we replace billions of years of evolutionary selection pressure with, well, a visual assessment by a human being.
A human looking through a microscope at 400 times magnification.
Right. We are assuming we know how to pick the best sperm. And many scientists argue that bypassing natural selection when you don't absolutely have to could inadvertently introduce genetically or structurally inferior sperm into the population.
Okay, so we are swapping a rigorous biochemical obstacle course for a beauty pageant judged by an embryologist.
That's a great way to put it.
But you mentioned workflow as well. How does the management of the lab itself dictate whether a patient gets conventional IVF or ICSI?
It comes down to risk mitigation and the sheer complexity of modern IVF cycles. Take pre-implantation genetic testing. or PGT.
Okay.
When patients want to test their embryos for chromosomal abnormalities, the embryologist eventually has to biopsy a few cells from the outer layer of the resulting embryo.
Right.
If that embryo is created using conventional IVF, there might still be thousands of accessory sperm stuck to the outside of the zona pellucida from the initial co-incubation.
Oh, wow. And those accessory sperm have their own DNA.
Exactly. So if the biopsy needle accidentally picks up one of those stray sperm along with the embryo cells, the genetic test results will be contaminated.
You might get a confusing read that blends the embryo's DNA with the DNA of a random sperm that failed to fertilize.
That is a massive operational risk for the lab. ICSI completely eliminates that risk. Because you only introduce a single sperm directly into the egg, the outside of the zona pellucida remains perfectly clean.
No accessory sperm.
Right. There are no accessory sperm to contaminate a future biopsy. And, furthermore, for a patient who only produces 1 or 2 eggs after an entire cycle of ovarian stimulation,
The stakes are incredibly high.
the clinic might feel the stakes are simply too high to risk a total fertilization failure. They'll default to ICSI to guarantee the sperm gets inside, prioritizing the immediate mechanical success over the theoretical benefits of natural selection.
It is a constant negotiation between biological ideals and clinical pragmatism.
It really is.
It is an incredible intersection of science and strategy. But before the embryologist can even load up the helicopter and deliver the sperm, they have to prepare the landing zone.
Right.
In conventional IVF, you want the egg's natural defenses intact. But for ICSI, you need total visibility. The terminology used in the lab is oocyte denudation,
Yes, denudation.
the literal stripping away of the egg's outer layers.
Because when an oocyte is retrieved from the human body, it is not the clean, smooth sphere you see in textbook illustrations.
It's not.
No, it is buried deep inside a massive, sticky, sprawling cloud of specialized cells called the cumulus oophoris.
A cumulus cloud.
Yeah, these cells nurse the egg during its development in the ovary, and in nature they provide the chemical signals that attract the sperm. This cloud is held together by a thick matrix of hyaluronic acid. It is incredibly viscous.
And looking at the micromanipulation protocols, it's very clear you cannot perform ICSI through that cumulus cloud.
It's impossible.
It's a matter of basic physics, right? If you try to drive a 5-micron glass needle through a thick, sticky cellular matrix, the needle will either clog, snap, or you'll just blindly push the egg around the dish without ever penetrating it.
You have to be able to see the precise boundary of the egg's membrane to puncture it safely.
So how do they get rid of it?
The denudation process is a 2-step combination of chemistry and mechanical friction.
Okay.
First, the embryologist transfers the entire cumulus oocyte complex into a microdroplet containing an enzyme called hyaluronidase.
Wait, isn't that the same enzyme the sperm uses?
Yes, it's actually the exact same enzyme that the sperm naturally carries in its acrosome cap. The lab is artificially applying the sperm's chemical weapon to digest the hyaluronic acid matrix holding the cloud together.
So it basically dissolves the glue.
Exactly. The fluffy cloud starts to loosen and fall apart.
But I'm guessing that's not enough on its own?
It's not. The enzyme alone isn't enough, and you can't leave the egg in the hyaluronidase for too long, or it will damage the oocyte itself.
Oh, that makes sense.
So after a brief chemical exposure, the embryologist moves the egg to a clear washing medium and uses specialized glass or plastic pipettes called strippers.
Strippers, okay.
The internal diameter of these stripper pipettes is meticulously calibrated to be just slightly larger than the oocyte itself, usually around 130 to 150 microns.
That's a tight squeeze.
It is. The embryologist rapidly aspirates and expels the oocyte in and out of this tight pipette. The mechanical shear force of passing through that tight opening physically scrapes the remaining corona cells off the zona pellucida.
Wow, the visual transformation must be striking. You go from this massive, opaque cellular cloud to a perfectly bare, translucent sphere.
It's very satisfying to watch, honestly.
But the real reason this step is so crucial isn't just about clearing a path for the needle, is it? It forces a harsh reality check on the actual status of the egg.
That's the real truth of denudation.
Because when the cumulus cloud is intact, the embryologist is effectively flying blind regarding the egg's maturity. The cloud hides the internal structures. Once you strip the egg naked, there is nowhere to hide. The embryologist has to visually confirm that the egg is actually ready to receive sperm.
And they are looking for a very specific microscopic marker.
The first polar body?
Yes, the first polar body. Its identification is a foundational moment in the ICSI workflow.
So explain what that actually is, biologically.
To understand what it is, we have to look at the unique mechanics of cellular division in reproductive cells, a process called meiosis.
Right, because normal cells divide differently.
Exactly. A normal human somatic cell has 46 chromosomes, but a sperm and an egg must each have exactly half that amount, 23 chromosomes, so that when they combine, the resulting embryo has the correct 46.
Right, because if they didn't have their DNA, you'd end up with an embryo with 92 chromosomes, which is, well, biologically incompatible with life.
It wouldn't work. The oocyte has to get rid of half of its genetic material before fertilization can occur.
So how does it do that?
It is a remarkable feat of asymmetric cell division. The oocyte duplicates its chromosomes, pairs them up, and then physically pulls the excess chromosomes to the very edge of the cell.
To the edge.
Yeah, and it pinches off a tiny blister-like extrusion just under the zona pellucida, dumping the unneeded half of its genetic material into this tiny sac.
And that sac is?
That discarded sac of DNA is the first polar body.
It is essentially the cell taking the genetic trash to the curb.
Exactly.
And when the embryologist looks through the microscope and sees that tiny blister sitting in the paravitrilline space, which is the gap between the egg's membrane and the outer shell, they know the internal genetic preparation is complete.
The presence of the first polar body indicates the oocyte has reached a stage called metaphase 2.
MI.
Commonly abbreviated as MII. This is the exclusive target for ICSI. The maternal chromosomes inside the egg are now perfectly aligned on a structure called the meiotic spindle, waiting for the sperm to arrive and trigger the final steps of division.
Okay, but the denudation process often reveals that the assumption of maturity was completely wrong.
Yes, it happens all the time.
A patient might have 20 eggs retrieved, all looking large and healthy inside their cumulus clouds. But after the embryologist strips them, they might find that only 12 of them actually have a polar body.
Right.
Wait, so an egg can look totally fine from the outside in conventional IVF, but when you strip it down for ICSI, you might find it's not even mature.
That's exactly right.
So what is the status of those other 8 eggs in that scenario?
Those remaining oocytes are immature, and they generally fall into 2 categories. You might see a large, distinct circle inside the cytoplasm called a germinal vesicle, or GV.
Okay, GV.
This means the oocyte is arrested at a very early stage of development. It hasn't even begun the process of discarding its extra chromosomes.
The trash is still in the house.
Yep. Alternatively, the GV might have broken down, but there is no polar body yet. This is called metaphase I, or MI.
So the genetic material is in transit, but the trash hasn't been taken out yet.
Exactly. And from a clinical standpoint, injecting a GV or an MI oocyte is just an exercise in futility.
Because the egg just isn't ready.
The cytoplasm physically lacks the biochemical machinery to process the sperm's DNA. If you force a sperm into an immature egg, the chromosomes will just hopelessly tangle and the cell will eventually degenerate.
That's biologically counterproductive.
Highly. For routine clinical ICSI, only mature MII oocytes are injected. The immature ones are typically discarded or, in some specialized cases, observed overnight to see if they mature in vitro, though their developmental potential is significantly lower.
So denudation provides total transparency. It tells the lab exactly how many viable targets they actually have.
Yes, but, and this is a massive caveat, there is a limit to that transparency, one that goes to the heart of the biological limitations we discussed at the top of the show.
Okay.
We can visually confirm structural maturity by looking at the polar body. We can prove the chromosomes have halved, but that visual marker tells us absolutely nothing about the oocyte's developmental competence.
Competence versus maturity.
The distinction between maturity and competence is perhaps the most frustrating reality of human embryology.
I can imagine.
Maturity is simply nuclear status. Competence is the sum total of the cell's molecular health.
Like what?
Does this oocyte have enough mitochondria to generate the ATP required to power early embryonic division? Are its maternal messenger RNAs properly transcribed and stored? Are its structural proteins correctly folded?
It's like evaluating a house from the outside.
Exactly.
The polar body tells you the foundation is poured and the walls are up, but you have no idea if the plumbing works, if the electrical wiring is safe, or if the roof will leak the moment it starts raining.
A morphologically perfect MII oocyte, complete with a beautiful polar body, can still be completely incompetent at a molecular level.
Wow.
The ICSI needle cannot inject cellular energy. We are selecting our target based on gross structural markers, hoping the invisible molecular machinery is functional.
It is a deeply humbling realization.
Very much so.
Even when we strip the cell bare and look at it under high magnification, the most important variables remain completely hidden from our eyes.
Yeah.
Okay, so we have isolated the target, we have we have a mature metaphase 2 oocyte. The landing zone is prepped. Now, the narrative shifts to finding the exact right payload to deliver into it.
The sperm hunt.
Exactly. And just like denudation changes the rules to the egg, ICSI completely changes the rules for how we handle the sperm. In conventional IVF, you process a sample, isolate the highly motile fraction, and dump hundreds of thousands of them into the dish.
It is population dynamics.
You're relying on statistics. But with ICSI, we are abandoning the population. We are engaged in a microscopic hunt for a single specific individual.
And depending on the quality of the semen sample, that hunt can take anywhere from a few seconds to several agonizing hours.
The embryologist isn't just looking for a sperm that is alive. They are evaluating gross morphology and motility in real time. I want to break down exactly what they're looking for under that 400 times magnification.
Okay, so morphologically, a human sperm is divided into three main sections: the head, the midpiece, and the tail.
What's the ideal look like?
The ideal candidate has a smooth, perfectly oval head. It shouldn't be too large, too small, tapered like a spear, or amorphous.
Why does the head shape matter so much?
Because the head contains the tightly packed nucleus, the paternal DNA, so structural abnormalities in the head often correlate with genetic issues.
Ah, okay. What about the rest of it?
Behind the head is the midpiece. This needs to be straight and slender. The midpiece is essentially the engine room. It houses the mitochondria that power the tail.
The battery pack.
Exactly. And the tail itself must be straight, uncoiled, and free of any cytoplasmic droplets, which are remnants of incomplete maturation.
And then there's the motility aspect.
Right.
A sperm can look structurally perfect, but be swimming in tight, rapid circles, or just twitching its head without making any forward progress.
Yeah, that doesn't help us. The embryologist is specifically looking for progressive motility. Sperm that are moving forward with purpose and strong, rhythmic tail beats.
Because that proves they have energy.
The speed and linearity of the movement are excellent proxies for the overall vitality of the cell. In a sample with normal parameters, an experienced embryologist can scan a droplet, mentally filter out the hundreds of abnormal sperm, and isolate a near-perfect candidate almost instantly.
But ICSI was designed for the most difficult cases.
Exactly. In a sample from a patient with severe oligoacidosis.
Say that 3 times fast.
I know, right? It means low count, poor movement, and high rates of abnormal shapes. In those cases, finding an acceptable sperm is a daunting task.
I can imagine the physical strain of that. An embryologist sitting in a dark room, hunched over a microscope, panning across endless fields of cellular debris, dead cells, and malformed sperm, just searching for one single cell that exhibits a faint glimmer of normal progressive motility.
It requires immense concentration and visual endurance. For testicular sperm extractions, the sperm have never learned to swim, they only twitch.
Just twitching.
The embryologist has to scour the biopsy tissue under the microscope to find those subtle twitches to confirm viability before they can even attempt an injection.
Okay, so let's say the hunt is successful. The embryologist spots a structurally normal, progressively motile sperm swimming across their field of view.
They found the one.
Now they have to catch it. And you can't just chase it around the dish with a tiny net. You have to perform a highly specific maneuver called immobilization.
Immobilization.
And this is the part of the ICSI protocol that feels the most counterintuitive to me.
Really? Why?
Well, you spend hours searching for the most vibrant, energetic swimmer, and the very first thing you do when you find it is intentionally damage it to stop it from moving. It sounds like trying to lasso a very fast, very tiny wild horse.
That's pretty accurate.
But why do we have to strike the tail? Doesn't breaking or compressing it damage the very thing we are trying to save?
You must strike the tail. The embryologist positions their sharp glass injection needle directly over the tail of the moving sperm, usually right in the middle or toward the end of the flagellum.
Okay.
They swiftly and firmly press the needle down, compressing the tail against the bottom of the plastic dish. You are not trying to sever the tail entirely, but you are applying enough blunt microforce to cause a distinct kink or a structural crimp.
It sounds incredibly violent at the cellular level. Why is this localized damage an absolute biological necessity?
There are two distinct reasons. One mechanical, one biochemical.
Let's do mechanical first.
Mechanically, you simply cannot inject a thrashing cell into the cytoplasm of an egg. The kinetic energy of a progressively motile sperm is formidable relative to the internal structures of a oocyte.
So it would just tear the egg apart from the inside.
Exactly. If you deliver a rapidly beating sperm into the egg, the flagellum will act like a microscopic blender. It will physically shred the meiotic spindle, disrupt the cytoskeletal matrix, and destroy the egg from the inside out.
Oh, wow. Okay. So immobilization removes the mechanical threat. The structural integrity of the egg cannot survive the physical movement of the sperm. That makes terrifyingly logical sense.
Right.
But you mentioned a biochemical reason as well, and this goes back to how ICSI bypasses the natural process.
This is a crucial concept. The membrane of a sperm cell is naturally stabilized. It is designed to protect the DNA payload during the arduous journey through the female reproductive tract.
It's wearing armor.
Basically. In nature, when the sperm finally binds to the zona pellucida of the egg, it triggers chemical changes that destabilize that membrane, culminating in the acrosome reaction and the eventual fusion of the sperm and egg membranes.
Right.
That fusion allows the internal contents of the sperm to flow into the egg. But in ICSI, there is no binding. There is no natural fusion. We are taking the entire sperm, intact membrane and all, and shoving it directly inside the egg.
So if we just leave the membrane intact, the sperm is essentially trapped in its own spacesuit.
Precisely. If you inject a perfectly intact sperm into an egg, the egg cytoplasm cannot access the paternal DNA, nor can it access a highly specific enzyme housed inside the sperm head called phospholipase Z or PLC-Z.
PLC-Z.
Yes, this enzyme is the biological key that actually wakes the egg up and triggers fertilization. We call it the oocyte activating factor.
So, by aggressively striking and kinking the tail, the embryologist purposefully creates micro-tears in the sperm membrane.
The physical trauma compromises the lipid bilayer of the membrane. It alters the permeability. It causes a sudden influx of calcium ions into the sperm, which mimics the natural destabilization process.
Ejects it.
It forces the sperm to transition from a state of motile transit to a state of structural breakdown. Once that permeabilized sperm is injected, the membrane breaks down rapidly, releasing the PLC-Z enzyme and exposing the paternal DNA to the egg's cytoplasm.
And if they don't do that?
If the embryologist fails to immobilize the sperm properly and injects it intact, the egg will never realize the sperm is there. It will not activate, and fertilization will fail.
You are intentionally triggering the destruction of the sperm's outer hull to release the cargo.
Yes.
So after the strike, the sperm is completely motionless. The embryologist maneuvers the tip of their glass injection needle near the sperm, applies gentle negative pressure suction, and draws the sperm up into the hollow barrel of the needle.
And the orientation is critical here. It is always aspirated tail first.
Tail first, why?
The sperm must be loaded into the needle so that the head is pointing out, closest to the sharp tip of the needle. When the injection occurs, the head, containing the DNA and the activating factors, will be the first thing deposited deep into the oocyte cytoplasm.
The payload is loaded. The targeting system is active. We have a naked, mature oocyte waiting, and a permeabilized, morphologically selected sperm-loaded tail first in a glass needle.
We're ready.
We are ready for the injection. But before we discuss the actual moment of puncture, we really need to take a step back and examine the engineering marvel that makes this even possible.
The micromanipulator rig.
We need to look at the microsurgery theater. The micromanipulation workstation is the absolute centerpiece of any modern IVF laboratory. It is a stunning piece of optical and mechanical engineering.
When you walk into an IVF lab, the ICSI rigs are the most intimidating pieces of equipment in the room.
I bet.
The foundation of the workstation is a high-powered inverted microscope. In a standard high school microscope, the light source is at the bottom, pointing up, and the objective lenses are on a turret looking down from the top.
That's what we all picture.
An inverted microscope flips that geometry entirely. The light source comes from above, shining down through the sample, and the heavy objective lenses are situated underneath the stage, looking up through the bottom of the transparent petri dish.
Which is an incredibly clever design because it leaves the entire space above the dish completely open and accessible. You have physical room to maneuver instruments without crashing into the lenses.
Exactly. And the stage itself is actively heated. The entire procedure is performed on a glass plate that is rigorously maintained at 37 degrees Celsius or 98.6 degrees Fahrenheit.
Body temperature.
Because these are human cells, they have no thermoregulatory capabilities. If they drop in temperature by even a few degrees for a sustained period, the meiotic spindle inside the egg, the delicate web of microtubules holding the chromosomes in place, can spontaneously depolymerize and fall apart.
Shatter.
The chromosomes will scatter, and the genetic integrity of the egg is destroyed.
So the temperature control is life or death.
Absolutely.
Flanking this heated microscope on the left and the right are the micromanipulators. These are the devices that actually translate the embryologist's hand movements into microscopic actions.
If you've ever seen a documentary featuring ICSI, you see the embryologist holding these large, thick metal joysticks, resting their hands heavily on armrests to eliminate tremors.
Because human hands are naturally unsteady.
Exactly. Even the most skilled surgeon has a microtremor. The micromanipulators use complex hydraulic or piezoelectric drive systems to scale down those human movements by an enormous factor.
How much of a factor are we talking?
Well, an embryologist might move the joystick a full centimeter, but the hydraulic lines translate that force, so the tip of the glass needle under the microscope moves only a single micron.
Oh, wow. You've got these massive joysticks translating human hand tremors into microscopic, perfectly still movements. The field of view is tiny, but the stakes for the patient are enormous.
It allows for a level of smooth, vibration-free, subcellular precision that the human body cannot achieve on its own. It effectively shrinks the embryologist down to the size of a single cell.
Attached to the ends of these manipulator arms, hovering over the dish, are the specialized tools of the trade, the micropipettes.
Right.
On the left side is the holding pipette.
The holding pipette is manufactured from a capillary tube of borosilicate glass. It is pulled over a high-heat filament until it stretches and snaps, creating a fine tip.
But it's not sharp, right?
No, the tip isn't left sharp. It is placed in a microforge, a tiny heated filament, where the sharp edges are melted and flame polished until they form a perfectly smooth, rounded, blunt end with a very wide outer diameter relative to its internal opening.
It looks like a microscopic glass donut.
That's a perfect description, and its sole function is stabilization. It is connected to a microinjector syringe filled with oil or air.
To create suction.
Right. By turning a dial, the embryologist can create a very gentle, highly controlled vacuum at the tip of the holding pipette. When brought against the side of an oocyte, that vacuum grabs the egg and locks it in place. It prevents the egg from rolling away when the injection needle pushes against it.
And on the right side of the manipulator setup is the injection pipette.
This is the weapon.
The spear.
It is also pulled from borosilicate glass, but instead of being polished blunt, it is driven against a grinding wheel to create a wicked beveled point, often with a microscopic spike at the very tip to aid in piercing the tough zona pellucida. It is incredibly fragile and incredibly sharp.
Okay, so that is the hardware. The microscope, the manipulators, the glass pipettes. But the environment where the cells actually reside during the procedure, the petri dish itself, is equally engineered.
It's not just a pool of warm water.
No. The embryologist constructs a highly specific microenvironment on the surface of the dish before the procedure even begins. Break down the layout of the ICSI dish itself.
The preparation of the ICSI dish is a meticulous protocol. Using standard pipettes, the embryologist places several tiny, distinct droplets of specialized culture media directly onto the surface of an empty plastic dish.
Microdroplets.
We are talking about maybe 5 to 10 microliters of fluid each. These droplets contain the necessary salts, buffers, and energy substrates to keep the cells alive outside the incubator. You typically have several droplets designated for holding the oocytes and a separate central droplet specifically for the sperm.
But if you just leave a 5 microliter droplet of water sitting on a warm stage at 37 degrees, it will evaporate into the ambient air of the laboratory in a matter of minutes.
It would vanish.
And as the water evaporates, the salt concentration in the remaining fluid spikes exponentially. The osmolarity skyrockets. The cells would instantly shrivel up and die from osmotic shock.
To prevent that catastrophic evaporation, the entire array of microdroplets is immediately submerged under a thick, continuous layer of highly refined mineral oil.
The oil overlay.
The oil seals the droplets off from the atmosphere. It prevents any evaporation, maintaining perfect osmolarity, and it also acts as a thermal buffer, holding the heat from the stage steady against slight air currents in the room. The microdroplets sit like tiny, isolated aquariums at the bottom of a pool of oil.
It is a brilliant physical barrier. But the engineering of the fluids goes even deeper, specifically in the droplet reserved for the sperm.
Because of how fast they are.
Right. If you drop a highly motile sperm into a droplet of standard culture media, it will swim furiously. It will cross the entire field of view in a fraction of a second. The embryologist would never be able to evaluate its morphology, let alone strike its tail.
They need a way to slow the sperm down without killing it.
And that is achieved by using a specialized, highly viscous fluid in the sperm droplet.
The viscous medium. The most common substance used is called PVP, or polyvinyl pyrrolidone.
I was reading about PVP. It is a large, synthetic, water-soluble polymer molecule. It acts like a thickener.
It fundamentally changes the rheology, the fluid dynamics of the microdroplet. Instead of swimming through water, the sperm are now trying to swim through microscopic syrup. The high molecular weight of the PVP creates significant drag on the sperm's flagellum. It severely dampens their velocity and restricts their movement patterns. They can still beat their tails, they are still alive, but they are moving in extreme slow motion.
It gives the embryologist the gift of time. In the PVP droplet, the embryologist can calmly pan the microscope, observe the slowed-down sperm, evaluate the shape of the head, confirm progressive intent, perform the tail strike, and aspirate the immobilized sperm into the needle.
The entire setup, the inverted optics, the hydraulic reduction of movement, the oil overlay, the viscous polymer fluid, it's all designed to grant a human being total mechanical control over a microscopic environment.
And once the sperm is loaded in the needle, the embryologist shifts the microscope stage over to one of the droplets containing a denuded, waiting oocyte. It is time for the main event.
The injection itself.
The injection. Let's walk the listener through the exact sequence of the injection itself. Slowly.
It's a choreographed sequence of micro-movements. It requires a level of muscle memory and spatial awareness that takes embryologists months, if not years, of rigorous training to perfect.
Step 1. The embryologist brings the oocyte into focus. It is floating freely in the microdroplet. The first critical action isn't to grab it, but to orient it.
Right. Positioning is everything.
The embryologist uses the blunt-holding pipette to gently nudge and roll the spherical egg until it is positioned exactly right. And they're using that first polar body, the genetic trash bag we discussed earlier, as their primary navigation beacon.
The positioning is non-negotiable. The embryologist typically aligns the polar body at either the 6 o'clock or the 12 o'clock position in the field of view, while the injection needle will be coming in horizontally from the right side at the 3 o'clock position.
Let me jump in and clarify this for the listener. Why do we care where the polar body is pointing when we inject? If the egg is a sphere, why can't you just puncture it anywhere?
Because the architecture inside the egg is highly polarized. The polar body sits on the surface, but right beneath it, just inside the cytoplasm, is the meiotic spindle.
And that's the danger zone.
Very much so. This is the fragile, web-like scaffold of microtubules that is actively holding the egg's chromosomes in a perfect alignment, waiting for fertilization. The spindle is the genetic heart of the oocyte.
And it is completely invisible under standard bright field microscopes used for routine ICSI. You can see the polar body, but you cannot see the spindle.
Precisely. Because you cannot see the spindle, you have to use the polar body as a proxy marker for its location. Studies have shown that the meiotic spindle is almost always located directly adjacent to or very near the polar body.
Okay, I see where this is going.
If the embryologist were to orient the polar body at the 3 o'clock position and drive the needle in from 3 o'clock, the sharp glass tip would spear directly through the meiotic spindle. It would shatter the microtubules and scatter the maternal DNA, instantly destroying the oocyte's viability.
By placing the polar body, and therefore the invisible spindle, at the very top or the very bottom, 12 or 6 o'clock, the embryologist ensures that the needle entering at 3 o'clock will travel through the widest expanse of empty cytoplasm, maximizing the distance between the lethal tip of the needle and the precious DNA.
It is a calculated trajectory of avoidance. Once the oocyte is perfectly oriented, the embryologist moves the holding pipette from the left, brings it flush against the zona pellucida at the 9 o'clock position, and engages the suction.
The negative pressure locks the egg firmly onto the polished glass rim. The oocyte is immobilized.
The target is locked. The embryologist shifts their visual focus to the right side of the field. The sharp injection needle, with the immobilized sperm resting just inside the tip, approaches the egg. The needle contacts the zona pellucida, the outer glycoprotein shell.
So how hard do they have to push?
The zona is relatively tough. The embryologist must advance the needle firmly and decisively. You can actually see the entire egg deform slightly under the pressure before the sharp spike at the needle fractures the glycoprotein matrix and slides through the shell.
So the needle is now inside the paravitline space, the gap between the shell and the egg itself. The tip is resting directly against the final barrier, the oolemma.
The plasma membrane.
This is the true border of the living cell, and this is where the physics of the injection become incredibly tense. The oolemma is not like a brittle eggshell. It is a highly elastic lipid bilayer.
When the embryologist pushes the needle forward into the cell, the oolemma does not immediately pop. Instead, it stretches.
It bends inward.
It wraps around the tip of the advancing needle, forming a deep microscopic funnel or tent. The needle is pushing deep into the center of the egg, but the membrane hasn't broken. The tip of the needle is still technically outside the cytoplasm, enveloped in this stretched membrane finger.
The embryologist is essentially pushing a glass pole into the side of a balloon, stretching the rubber inward without piercing it. How do they actually force the break? They can't just keep pushing, or they will drive the needle entirely through the other side of the egg.
No, they have to use fluid dynamics to break the tension. While the membrane is deeply tented over the needle, the embryologist applies a sudden, sharp pulse of negative pressure suction to the injection syringe.
They suck.
They attempt to suck a tiny volume of the egg's internal cytoplasm into the needle. The combination of the extreme mechanical stretch over the glass tip, coupled with the sudden internal vacuum pulling the membrane inward, finally causes the lipid bilayer to yield.
The tension breaks, the balloon pops.
The visual feedback of this break is subtle but unmistakable. The embryologist watches the fluid inside the needle. Suddenly, the cytoplasm, which looks slightly granular, rushes rapidly into the bore of the injection needle, mixing with the small amount of culture media holding the sperm.
Oh, wow.
That sudden, free-flowing aspiration is the absolute confirmation that the oolemma has been breached. The needle is finally inside the cell.
It is a microscopic moment of truth. The door is forcefully kicked open, and the embryologist cannot hesitate. The longer that needle sits inside the cell, the more the internal pressure dynamics are disrupted.
The action is immediate. The embryologist smoothly reverses the pressure on the syringe. They push the aspirated cytoplasm back down the needle, followed directly by the single sperm, depositing them precisely in the center of the oocyte.
So gentle.
And the embryologist must be extraordinarily careful to deposit as little of the PVP fluid as possible, as excess polymer can be toxic to the internal machinery of the egg.
The payload is delivered. The sperm is inside the living room. Now, the embryologist has to get the needle out without tearing the cell apart on the exit.
The withdrawal is just as critical as the entry. The embryologist smoothly and quickly pulls the injection joystick back. The needle slides out of the cytoplasm and retracts through the hole in the zona pellucida.
And what happens to the hole?
If the oocyte is healthy and the oolemma is sufficiently elastic, the tiny puncture wound in the lipid membrane will spontaneously fuse and seal itself closed almost instantaneously. The embryologist releases the suction on the holding pipette, and the injected oocyte floats free.
So, summarizing the step, it's not just stabbing the egg. It's controlled entry, controlled deposition, and controlled exit. The entire physical intervention takes less than a minute in the hands of a skilled operator.
Yes, the true goal is minimizing trauma. A successful injection is one where the oocyte barely registers the intrusion.
But even with perfect microsurgical technique, we cannot lose sight of the reality. You have just shoved a rigid glass spear into a highly sensitive, single living cell.
It is a trauma.
You have disrupted its membrane, altered its internal pressure, and injected foreign fluid and a permeabilized sperm into its cytoplasm. And that physical trauma leads us to the immediate high-stakes aftermath.
The fallout.
Let's talk about the fallout.
Yeah.
Because the procedure itself is only the first hurdle. The embryologist moves the injected eggs out of the microdroplets, washes them, places them in fresh culture media, and puts them safely into the dark, warm environment of the incubator. And then they wait.
The waiting is the hardest part.
And the first few hours are critical because sometimes the mechanical trauma is simply too much for the cell to handle. Let's explore what happens immediately after the pipette is withdrawn.
The most immediate technical risk of ICSI is post-injection degeneration. The oolemma of an egg is not a uniform material. Its elasticity and strength vary wildly from patient to patient and even from egg to egg within the same cohort.
So some are fragile.
Very. Sometimes an embryologist will encounter an egg with an incredibly fragile membrane. It doesn't tent smoothly, it snaps unpredictably. Or, conversely, an egg membrane might be so rigid that the embryologist has to apply massive aggressive suction to force the break, tearing a jagged hole.
And when the needle is withdrawn from a fragile or badly torn membrane, it doesn't seal itself.
It fails to fuse. The internal pressure of the egg forces the cytoplasm to leak out through the puncture wound into the paravitelline space.
It bleeds out.
The cell literally bleeds out its internal contents. The delicate osmotic balance is destroyed, the membrane collapses, and the oocyte undergoes rapid lysis and death. The embryologist might look at the dish an hour later and see a dark, shriveled remnant of what was a healthy cell.
That is a devastating loss, and it underscores a hard truth. The physical survival of the oocyte is the very first biological checkpoint of ICSI. The sperm being inside is irrelevant if the egg doesn't survive the trauma of the delivery method.
Exactly. Survival is the first success, fertilization is the next.
But let's assume the best. Let's assume the ulema is resilient. It seals perfectly, the cell survives the trauma, and it looks beautiful resting in the incubator. We have successfully bypassed the journey, breached the shell, and hand-delivered the sperm. A lot of patients, and frankly a lot of the general public, assume that at this precise moment, fertilization is a guaranteed done deal. The sperm is inside, therefore an embryo will form.
And that is the most pervasive, fundamental misunderstanding of the ICSI procedure.
Really?
ICSI guarantees mechanical delivery. It guarantees proximity. It absolutely does not guarantee biological integration. We have forced the two cells into the same physical space, but we cannot force them to actually communicate and fuse their genetic material.
This goes back to the concept of oocyte activation that we touched on during the sperm immobilization step. We kink the sperm tail to release the PLC-zeta enzyme into the egg. That enzyme is supposed to trigger the alarm clock.
It initiates a massive, complex signaling cascade. The PLC-zeta enzyme interacts with the egg's internal structures to trigger the release of calcium ions from intracellular stores.
Calcium ions.
This isn't just a single event. It creates a rhythmic, oscillating wave of calcium sweeping across the entire egg. This calcium wave is the universal biological signal that tells the egg, you have been fertilized, resume meiosis, finish your cellular division, and start forming ponuclei.
Let me push back on this perceived omnipotence of the procedure. So we've done all this. We bypassed the journey, bypassed the outer shell, hand-delivered the sperm, and the egg can still just basically hit the snooze button and fail to activate.
Yes, it happens. The activation cascade simply fails to initiate. This can be due to a deficiency in the sperm's PLC-zeta, or it can be a failure in the egg's calcium storage and release mechanisms.
So what happens then?
The sperm sits motionless inside the cytoplasm, the egg never receives the biochemical signal to wake up, and fertilization completely fails. The cells remain inert until they eventually degrade.
Wow. And even if the calcium wave does occur, even if the egg successfully activates and starts the process, we are still held hostage by the developmental competence of the oocyte. We talked about this when looking at the polar body.
We did. The structural changes required to process the sperm DNA and initiate the first embryonic cell divisions require vast amounts of cellular energy. That energy is supplied by mitochondria in the form of ATP.
Right.
If the oocyte is genetically or metabolically deficient, if it simply doesn't have the mitochondrial reserves or the correct messenger RNAs stored up from its time in the ovary, it will physically run out of gas.
It's a mechanical analogy, but it's precise. You can use the most advanced robotic system to insert the key perfectly into the ignition. You can turn the key, the starter motor might even crank. But if there is no chemical energy, no ATP fuel in the tank, the engine will never start. The embryo will arrest.
And the final, inescapable biological limitation rests with the sperm itself. Chromatin integrity.
The DNA.
The entire point of ICSI is to deliver the paternal DNA. But the embryologist selecting the sperm under the microscope can only evaluate its external shape and its tail movement. They cannot see the microscopic strands of DNA packed tightly inside the sperm head.
And sperm DNA is highly vulnerable. Factors like advanced paternal age, smoking, environmental toxins, or oxidative stress in the male reproductive tract can cause severe DNA fragmentation. The DNA strands literally break apart.
A sperm with highly fragmented DNA can look absolutely beautiful on the outside. It can swim perfectly. The embryologist will confidently select it and inject it. The egg might survive the injection. The egg might activate.
But then what?
Once the sperm head breaks down and exposes that fragmented, shattered genetic blueprint to the egg, the biology eventually recognizes the catastrophic errors. The resulting embryo will almost inevitably stop growing, usually around day 3 of development, when the embryonic genome attempts to turn on and read that corrupted code.
The ICSI needle is a marvel of physics, but it is blind to genetics. It cannot fix broken DNA, and it cannot manufacture cellular energy. ICSI solves the problem of access, but it does not guarantee outcome. The biological competence of the oocyte and the genetic integrity of the sperm are ultimate limiters that no glass needle can fix. Understanding these strict limitations naturally forces a reevaluation of how ICSI is viewed by the public versus how it is understood in the lab. We need to frame ICSI against conventional IVF and directly dismantle the myths that have grown around it.
It is vital to do so because in popular culture and often in patient forums, ICSI is spoken of as a premium upgrade, a silver bullet that somehow fixes all infertility.
Right, like it's the VIP lane.
Exactly. To understand why it isn't, we have to look clearly at what conventional IVF is designed to do. Conventional IVF is an intense, rigorous, biological functional test.
When you place 100,000 sperm in a droplet with a cumulus enclosed egg, you are subjecting every single one of those sperm to a grueling decathlon. You are testing their sustained kinetic energy to migrate through the fluid. You are testing the integrity of their membrane receptors to recognize and bind to the specific glycoproteins on the eggshell.
You are testing their biochemical ability to initiate the acrosome reaction and release the exact right enzymes. And you are testing their sheer physical stamina to drill through the zona pellucida.
It is millions of years of evolutionary pressure recreated in a petri dish.
Only a sperm that is fundamentally sound in its metabolism, its receptor chemistry, and its physical structure will pass every test and reach the cytoplasm. Conventional IVF allows the biology to sort itself out, eliminating the weak or defective cells naturally.
ICSI, however, replaces that entire biological obstacle course with a technical intervention. The embryologist looks at the sperm swimming in the viscous PVP droplet, notes that the head looks generally oval and the tail is moving forward, and says, you are the one.
The embryologist is making a macrovisual selection that bypasses every single functional test of the sperm's actual biochemical competence. We assume that gross morphology correlates with genetic integrity, and while statistically there is a relationship, it is far from an absolute guarantee.
Conventional IVF is an audition for the sperm. It forces every actor to perform a brutal, exhaustive audition. They have to prove they can memorize the script, hit their marks, project their voice, and perform the choreography perfectly under pressure. The one who nails every aspect gets the part.
That's right.
ICSI cancels the audition and just hands one sperm the lead role. The director walks into the waiting room, points to an actor because he happens to be wearing the right costume, and puts him on stage. But the play still might be disaster if the script, the genetics, is bad.
Which perfectly dismantles the first major myth we encounter, the belief that ICSI guarantees fertilization.
The reality is that ICSI only guarantees spatial access. It places the actor on the stage. If the actor's script is corrupted by DNA fragmentation, or if the theater itself, the oocyte, has no power to turn on the lights, the play simply doesn't happen. Fertilization fails.
The second pervasive myth is that any retrieved egg can be injected using ICSI. Patients will see they had 15 eggs retrieved and expect 15 ICSI procedures.
But the reality is dictated by the denudation process. Only the mature metaphase oocytes, the ones that have physically demonstrated nuclear readiness by extruding the first polar body, are routinely injected.
The embryologist is forced to discard the immature GV or MI oocytes because injecting them is biologically useless. The starting number of eggs almost always drops before the needles even come out.
And the final, perhaps most dangerous myth, is that once a sperm is selected and injected, its inherent quality no longer matters. Because the lab did the work of getting it inside, the sperm's job is done.
The reality, as we have exhaustively discussed, is that viability, metabolic health, and genetic integrity matter immensely. You cannot force a broken machine to function simply by placing it inside a new box. The molecular reality of the cell always asserts itself.
Intra-cytoplasmic sperm injection is undeniably one of the crowning achievements of reproductive medicine. The ability to build hydraulic systems that scale down human motion, to pull glass into microscopic spheres, and to physically manipulate single human cells without destroying them is a triumph of engineering and human precision.
It has allowed millions of people to build families who 30 years ago would have had zero biological options. It is awe-inspiring.
But we must remain grounded in the science.
It is an intervention. It is not a triumph over biology. The underlying biology, the invisible genetics, the molecular energy reserves, the complex enzymatic cascades always, without fail, has the final say in whether life begins.
Not a triumph over biology. That is a stark, grounding perspective. As we wrap up this deep dive, I want to leave you, the listener, with a final provocative thought to mull over. When you look at photographs or videos of the ICSI procedure, that moment of injection, the needle piercing the shell, the cytoplasm rushing in, the tiny sperm being deposited, it feels incredibly dramatic.
It does. It feels like the climax.
It feels like the grand climax of the entire IVF laboratory process. It is the absolute peak of human physical intervention in the creation of a human embryo. We force the door open, we drag the guest in the living room, and we step back.
We do everything in our mechanical power to initiate the cascade.
But biologically, that dramatic injection is just a midpoint. The intervention ends the second the needle is withdrawn. The embryologist closes the heavy door of the incubator, and the laboratory goes quiet. We've forced the components together, but now we have to wait in the dark.
We have to wait to see if the alarm goes off.
We have to wait to see if there's energy in the cell. We have to wait to see if the invisible biology actually takes hold and begins to dance.
The machinery of life has to decide to turn itself on.
I want to warmly thank you for joining us on this incredibly complex, microscopic journey today. We have traveled from the sweeping biological obstacle course of conventional IVF down to the viscous microdroplets and glass spears of the ICSI dish.
We've explored the very limits of what a laboratory can actively control, but this journey through the lab is far from over.
It certainly isn't, because as we just established, the injection is only the midpoint. The real answer, the proof of whether the biology actually accepted our mechanical intervention, comes hours later. Next time, we shift our focus from the physical procedure to the biological proof. Join us for episode 7, where we look at the fertilization check, searching for pronuclei, polar bodies, and the earliest signs that an embryo is beginning to form. Until then, keep looking deeper.